So we finished this semester with the last chapter, which is chapter 7. This is about Fourier Transform. So we're gonna do this chapter briefly and be very well, and we're gonna do all the property of Fourier Transform pretty fast, so that we go and do PDE and go and do its application to partial differential equation. Since we have only 1 week, we cannot go into too much details. So let's see. So definition, we say f is an L1 of R if and only if integral from minus infinity to plus infinity of absolute value of f of x dx is less than plus infinity. And we say f is an L2 of R if and only if integral from minus infinity to plus infinity absolute value of f of x squared dx is less than plus infinity. So remember, if I have a function given a function f, we want to divide it into its contained frequency. So we have a signal, and we have to divide the signal into, which part of the signal has such frequency, which part of the signal has different frequency. And we saw when we have a 2 pi periodic function, then we had 2 pi, we had the frequency which were e to the I n x, which was then 2 pi over n, because these were the period of e to the I n x, yes, which is 2 pi over, this is the period t equal 2 pi over n, yes, so the frequency was n over 2 pi. But if the function is not 2 pi periodic, then I want to see all the frequencies that are contained in my signal. So we write it as a sum, of e to the I omega x. So I want to see the part of my function whose frequency it is at e to the I omega x. Okay. So the Fourier transform of f is defined then as follows: f hat of omega equal 1 over square root of 2 pi, is just a constant to normalize, integral from minus infinity to plus infinity. Remember, if I want the i's coordinate, I dot with I. Remember, if I want the j coordinate, I dot with j. Then f hat of omega will be what? And this is the Fourier of f is equal minus infinity to infinity, you dot with e to the I omega x, which means e to the I omega x bar here, e to the minus omega x dx, and this is for all omega in R. So now the Fourier coefficients, which is the multiple of e to the I omega x, is defined for all frequencies omega. Okay, remember my function f is defined in R. In fact, we say f is an L1 of R. It should be integral. But the way to define, really to start defining a Fourier transform, we start with functions that decrease very rapidly to 0, and then we generalize this to L1, and in fact you can have Fourier transform of function in L2 of R. This is still okay. But whenever you think about Fourier transform, think about Fourier transform of function that decay very fast to 0. Now, if we sum the frequency, so this is like your Cn. Remember, your Cn, which is C of n, was what? Was 1 over pi, which was a constant, integral from minus pi to pi of f of x e to the minus I nx. Okay. Okay. This was my constant C sub n. Let me check. I think there's a 2 maybe. Okay, so your Cn was 1 over 2 pi. Yes. Okay. Sorry about that. So yes, your Cn was 1 over 2 pi this. Forget about the constant. You were doing the dot product with f with e to the in x. I mean, your signal was 2 pi periodic. Yes, this was your signal. But now if I have a function on R, I want to divide it of all of its contained frequency. Then your Fourier now, it becomes C of omega. This is now a function, which I call f hat of omega, is equal to 1 over radical 2 pi. Forget about the constant. Again, the constant is just for normalization. F of x e to the minus I omega x. Now here in the Fourier series, how did I reconstructed my function? Your f was summation Cn e to the I n x. So now how you construct your function back? Now if we sum the f hat, we should recover little f. But now f hat is defined for all omega. So this f hat is the representation of f in the frequency space. So the Fourier inverse of f hat is equal 1 over square root of 2 pi. This is my constant, and now I'm adding all my frequency, which means e to the, this is Cn e to the I n x, f hat of omega e to the I omega x, but this is sum over all omega in R, so it's now an integral, and we get this. So as in the Fourier series case, if f is PC1 of R and L1, then 1 over, then Fourier inverse of f hat, which is 1 over square root of 2 pi of integral from minus infinity to plus infinity f hat of omega e to the I omega x dx d omega. This is when you do a Fourier inverse, you go back to physical space. This is equal to f of x if x continuity point equal f of x minus plus f of x plus over 2 if x discontinuity point. Okay. But I will not emphasize here a lot, so we will assume from now on that the value of f at this continuity point is f of x minus plus f of x plus over 2, i.e. the Fourier inverse of f hat will be equal to f. Okay? So I mean, if a point is a discontinuity point, I assume my f is already the average of the left limit and the right limit. So we get what? F hat of omega is equal 1 over square root of 2 pi integral from minus infinity to plus infinity f of x e to the minus I omega x dx. This is my function in frequency space. If I want to re-get my function, I get f of x. So this is if f is in PC1. F of x, well, even in more general cases, okay, so I will give you the theorem in general. It's 1 over square root of 2 pi integral from minus infinity to plus infinity of f hat of omega times e to the I omega x d omega. Okay, this is even if it's an L1. The Fourier inversion formula works if f is, so this is true in general if f and f hat belongs to L1 of R, then this is usually works. Okay, so now we will start with some example, and then we're gonna, so example. So find, let sigma x be equal to 1 when absolute value of x smaller than 1 is equal to 0 when absolute value of x bigger than 1. What about at discontinuity point? At discontinuity point, always assume your function to be the midpoint. So this is at discontinuity point. Okay. Okay, so let's see. And then let's calculate sigma hat of omega, means the Fourier transform of sigma, and conclude the integral from 0 to positive infinity of sine t over t dt. Let's see. Okay, so solution. What is sigma hat of omega? It's equal 1 over square root of 2 pi integral over r. This means from minus infinity to positive infinity. This is equal to sigma of x e to the minus I omega x dx. And then what? And then I get sigma hat. Now sigma x is equal to 0 except when x between minus 1 and 1. So this is equal to square root of 2 pi. I can divide this into integral from minus infinity to minus 1 plus from minus 1 to 1 plus from 1 to infinity. But this is equal to 0 and this is equal to 0. So this is equal 1 over square root of 2 pi integral from minus 1 to 1. What is sigma x here? It's equal to 1 times e to the minus I omega x dx. And now this is equal 1 over square root of 2 pi e to the minus I omega x over, you are integrating respect to x, over minus I omega when x is between minus 1 and 1. And this is equal 1 over square root of 2 pi times, let's say, and here I have e to the minus I omega minus e to the minus I omega over minus I omega. Here you have a plus. And then you get, this is equal 1 over omega square root of 2 pi e to the I omega minus e to the minus I omega over I. But now this is like a sine, but I should have a 2 here to get a sine. So this is equal 2 over omega square root of 2 pi times sine omega. Now 2 over square root of 2 is just square root of 2, yes? So this is equal square root of 2 over pi, everything is inside the square root, times sine omega over omega. Okay? And now I know the following. So this is a function that is continuous, PC1. So I can apply the Fourier inverse formula. So this is the Fourier, okay, sigma hat of omega. Now you will see on Moodle there will be few things published on posted. There will be posted a formula sheet which is usually given in the exam, where it has a table of Fourier transform. Okay, you should know how to get the Fourier transform of functions, and there are some functions that you don't have to prove it every time. I'm giving this to you on the table, and there's a formula sheet, and there's some folder that has exercises. Okay, so now we are exercises which are about application of Fourier transform on partial differential equation. At the end of this chapter, we will solve this extra sheet. But now we'll emphasize only on properties of Fourier transform. So now this is sigma hat of omega. Now by Fourier, now the question is to calculate this integral. Okay, but I know now from the Fourier inverse formula that 1 over square root of 2 pi integral from minus infinity to plus infinity sigma hat of omega e to the I omega x d omega. So if I add my frequencies, I should recollect my function, which is equal to what? Which is equal to 1 when absolute value of x smaller than 1, is equal to 0 when absolute value of x bigger than 1. What about when x equal plus or minus 1? This will be equal to 1/2. Next. And now let's see what the left-hand side is. So this is 1 over square root of 2 pi, integral from minus infinity to plus infinity. I'm just calculating the left-hand side. Sigma hat of omega is square root of 2 over pi sine omega over omega times e to the I omega x d omega. And this is equal. Radical 2 cancels out. Radical pi times radical pi, you get 1 over pi integral from minus infinity to plus infinity. I want to get only sine t over t. Yes, remember the question? I want to get only integral sine t and t. So this is sine omega over omega. E to the I omega x is cosine omega x plus I sine omega x dx d omega. And this is equal 1 over pi integral from minus infinity to plus infinity. Let's write it like this. Real part sine omega over omega cosine omega x dx plus I times 1 over pi integral from minus infinity to plus infinity of sine omega x over omega sine omega, sorry, let's leave some space. So this is equal 1 over pi integral from minus infinity to plus infinity. I'm writing as real part sine omega over omega times sine omega x d omega. Now this is equal to 0. Yes, why? Because this is odd in omega. Replace omega by minus omega, you get a minus sign. So we conclude, even if not, but I know, even if you are doubting, even if it's not odd, you know that this is equal to 0. Why? Because now this is a complex number. This is its real part, this is its imaginary part. And I know that it's equal to the following for all x. But this is real, which means this sum should be real, which means the imaginary part should be 0. This is one way to see it. Or, I mean, this is a complicated way to see it. Or I can see only that this function is odd, so it vanishes. So I conclusion, 1 over pi integral from minus infinity to positive infinity sine omega over omega cosine omega x dx. And I know that this is equal to minus 1 if absolute value of x smaller than 1. Sorry, 1. 0 if absolute value of x bigger than 1. And half if absolute value of x equal to 1. Now I want integral sine t dt. So I take x to be equal to 0. Then you get 1 over pi integral from minus infinity to plus infinity sine omega d omega here. Sine omega over omega d omega. When x equals 0, so this is my, when x equals 0, the image is 1, equal to 1. Then integral from minus infinity to plus infinity of sine omega over omega d omega equal to pi. In fact, I could get it from the very beginning, but I wanted to show you splitting into real and imaginary. You can take from here, take x to be 0. Okay? From the very beginning. You can see it. I mean here, you could see it here. If you take x to be 0, you will be done, yes? Because then e to the 0 is just 1. So this is pi. But now the question is, what is integral from 0 to positive infinity of sine t over t dt Well, this is equal 2 times from it's equal 1/2 integral from minus infinity to positive infinity sine t over t dt. And why is that? Because this is even function, which is equal pi over 2. So now you can calculate difficult integral, yes? Sine t over t is equal pi over 2. Like the same way you used to calculate difficult sum in the Fourier series chapter. So another example. Okay. So calculate, this is also in the table, the Fourier transform of e to the minus absolute value of x. So you see all the function we're going to take, so this is e to the x, this is e to the minus x, and then this is an even function. So this will be, so all the function I'm going to take will vanish at 0 pretty fast, yes. And then conclude integral from minus infinity to plus infinity of cosine t over t squared plus 1 dt. Calculating this integral using, the calculus trick doesn't work, by the way. Okay, so you need something fancy, either complex integration, which you can take into 2.7, or you can take something even fancier, which is Fourier transform that we're learning in this course. Well, so I take f of x is equal e to the minus absolute value of x, then f hat of omega equal 1 over square root of 2 pi integral over r e to the minus absolute value of x times e to the minus I omega x dx. Okay, and now this is equal 1 over square root of 2 pi. My function is divided into two pieces. X is negative, x is positive, although they are discontinuous, but due to the absolute value. So this is minus infinity to 0 e to the x is negative, so absolute value of x, is equal to minus x if x is negative, is equal to x when x is positive. So this will be e to the x, e to the minus I omega x dx, plus integral from 0 to infinity e to the minus x e to the minus I omega x dx. Okay, so this is equal 1 over square root of 2 pi integral from minus infinity to 0 e to the, I want to integrate back to x, so I take x common factor 1 minus I omega dx plus integral from 0 to infinity e to the minus x, or e to the x into minus 1 minus I omega dx. Now let's calculate each of these integral. I will take x to be minus infinity. I don't like it, so I will take it as a limit. So integral from minus infinity to 0 e to the x into 1 minus I omega dx. This is equal limit as r goes to positive infinity of integral of minus r to 0 of e to the x into 1 minus I omega dx. Now this equals the limit as r goes to infinity of, now integrate this, it will be e to the x into 1 minus I omega over 1 minus I omega between minus r and 0. And this is equal the limit as r goes to positive infinity. At 0 this is 1, so 1 over 1 minus I omega minus e to the minus r into 1 minus I omega over 1 minus I omega. Now what happened when r goes to infinity for this one? Well, it will be e to the minus r is the minus infinity. You would think it's 0, but yes, you still have to justify it because this is infinity times a complex number. It's not very clear. So this is the same. What is e to the minus r 1 minus I omega? This is equal e to the minus r times e to the minus I omega plus e to the I omega. Okay. Then absolute value of e to the minus r into 1 minus I omega is equal to e to the minus r, because absolute value of e to the I omega is equal to 1. And now this goes to 0 as r goes to infinity, and this implies that e to the minus r into 1 minus I omega, oops, sorry. So e to the minus r times e to the minus omega, this goes to the absolute value. If the absolute value goes to 0, this means the function, the complex number, goes to 0. Because if, so absolute value of the n goes to 0, if and only if the n goes to 0. This is where the n is the sequence of complex numbers. Okay. How I did it? I divided into, I wrote into complex term, e to the minus r, e to the I omega. The absolute value goes to 0, so this goes to 0. So conclusion, the integral from minus infinity to 0, e to the x times 1 minus I omega dx is equal 1 over 1 minus I omega, which is this, because this goes to 0. Now I still have, now what about, so I calculated this integral. What about the following one? I have integral from 0 to infinity e to the x times 1 plus minus 1 minus I omega, minus 1 minus I omega dx. This is by definition is the limit as r goes to infinity, integral from 0 to r, e to the x into minus 1 minus I omega dx. Okay, and this is equal the limit as r goes to infinity of e to the x into minus 1 minus I omega over minus 1 minus I omega between 0 and r. And this is equal limit as r goes to infinity of e to the r minus 1 minus I omega over minus 1 minus I omega plus, because minus minus, 1 over 1 plus I omega. Now again, e to the r into minus 1 minus I omega, this is equal e to the minus r, e to the minus I omega. So absolute value of e to the r into minus 1 minus I omega, this is equal then to e to the minus r. Why? Since e to the minus I omega equal to 1, and this goes to 0, then e to the r into minus 1 minus I omega goes to 0 as r goes to infinity. And then we get that the integral from 0 to infinity e to the x into minus 1 minus I omega dx, this is equal, this goes to 0, so this is the only surviving term, 1 over 1 plus I omega. So conclusion, the Fourier transform f hat of omega is equal 1 over square root of 2 pi 1 over 1 minus I omega plus 1 over 1 plus I omega. And this is equal, let's do common denominator. So this will be 1 minus I omega into 1 plus I omega into 1 plus I omega plus 1 minus I omega. And this is equal 1 over square root of 2 pi of 2 over, you know that a plus ib times a minus ib, this is equal a square plus b square, because this is a square minus ib square. So this is 1 plus omega square. Now 2 over square root of 2 is square root of 2, so this is square root of 2 over pi over 1 plus omega square. And this is f hat of omega. That's how I calculate the Fourier transform. Okay. Now the question is what? Is to calculate the integral of cosine t over t squared plus 1 from minus infinity to plus infinity. So this is 1 plus omega squared. So it seems I have to use Fourier inverse. So by the inversion formula, I have integral 1 over square root of 2 pi, and t from minus infinity to infinity. Now I add up the Fourier 1 over 1 plus omega square times e to the I omega x d omega. I'm adding the frequency. I should get back e to the minus absolute value of x. This is a continuous function that vanishes pretty fast, okay? This is by the Fourier inversion formula. Now radical 2 over pi, radical 2 over pi, so radical 2, radical 2, so I get again 1 over pi, integral from minus infinity to plus infinity. Again, you divide it into cosine and sine. 1 over 1 plus omega square cosine omega x d omega plus I integral from minus infinity to plus infinity 1 over 1 plus omega square sine omega x d omega, and this is equal e to the minus absolute value of x. Okay, or I only want this, so I can skip this one maybe here. Let x equal to 0 from the very beginning, and then you get 1 over pi integral from minus infinity to plus infinity. Oh no, this won't work if you take x equals 0. You will not get a cosine. Sorry, the question is to calculate the one with cosine. Again, so let's rewrite this. So this is 1 over pi integral from minus infinity to plus infinity. 1 over 1 plus omega square cosine omega x d omega plus I integral from minus infinity to plus infinity 1 over 1 plus omega square sine omega x d omega, and this is equal e to the minus absolute value of x. Now this is a complex number and this is the imaginary part, so this should definitely vanish. This is equal to 0, and you can notice that this is odd in omega. This will help you also. Then you get 1 over pi integral from minus infinity to plus infinity 1 over 1 plus omega square cosine omega x d omega equal e to the minus absolute value of x. Now I want x to be, I take x to be equal to 1 because I want cosine t over t squared plus 1, and then you get 1 over p 1 over pi integral from minus pi to pi cosine omega over 1 plus omega squared d omega is equal e to the minus 1 minus infinity. Wow, minus infinity to infinity. So integral over r of cosine t, now it's a dummy variable, I mean, over t squared plus 1 dt is equal to pi over e. Very nice integral. Okay. Okay. So I'll stop this video now. In the next video, we're going to discuss the property of Fourier transform.